Fine. Oh, but you don't see the screen.
And sir, is the exam open book or closed book?
Closed book, of course. It's closed
Like
book exam.
closed book and closed notes.
Closed book, closed notes, closed internet. Okay.
I mean, how can you open Zoom with
One
closed
second.
internet?
I will stop. How can you? No, no, I said,
How?
yeah, you can close internet. You closed Google, I mean. That's what I mean. It's not closed internet. How will I check whether you have the internet or not? It's not possible for me. It's okay.
So the exam full marks will have 100 marks, right?
Yes.
And like so I saw your analysis stream exam paper. There are choices. So will there be choices
Yes,
in
there
this?
will be a lot of choices. Yes.
And if you
A
do
lot of
more,
choices. I mean,
and if
I hopefully a lot of choices. Yeah.
and if I do more than what is required, so will the only the first few will check, or you will check the all of them, and the
No, if
total
you
will be
do
added,
more
and
than required, you will get 100 marks. Don't worry. There is nothing like first one or it's not school exam. I mean, you will
okay, okay,
get if whatever you have done right, that will be counted.
okay,
Maximum mark will be counted. I will correct all the questions. Okay. So if you get 124, you can score 100 marks. That's all. You can write up to 150 marks, no problem. Okay, there is nothing like that. I mean, those things are gone with your school. Okay. So this is the assignment.
and other thing is that the 15 minutes like for our midterm exams we are given like 1 or 2 scans. So 15 minutes might be too low. Can you extend to 30 minutes or something? The scanning time.
Okay, no, the point is the exam should be for 3 hours. I'm giving three and a half hours. Okay, and
Well, like for example, our for the midterms, like all of our core course midterms, we are given like honor just for scanning.
1 hour
So,
for scanning. I never heard
but
it.
so for honor it's only about 30 minutes. So that been like 15 minutes is a bit too lot to scan it legibly because the
Okay, I
things
can.
might
Okay, you
be
can go up to 5:30. It's okay. But I mean, in my son's school, they
okay.
give only 10 minutes to scan. So that's why I just decided like that. I don't know about
Okay,
other
okay,
exams what they have done. So I have only seen my son attending my school. In his exam, they are
okay.
giving only 10 minutes. So that's why I gave 15 minutes. It's okay. Half an hour is also okay. No problem. That's not a problem. I mean,
And just to confirm the syllabus
syllabus
is
is
in this
still Fubini's theorem.
the product measure and Fubini's theorem.
Yes, Fubini's
Okay,
measure theory basically.
okay,
Okay, okay. Shall we start? I think it's getting
yeah,
recorded.
okay,
It's
okay.
getting recorded. So yeah. So the assignment I gave, I just there was some. Uh, I mean, Anupam raised some doubts, so that's why I have written it clearly. It's the same thing. Instead, how do you define the sum and all those things? So I have defined it in the. This is the assignment which I have given in the last class. I'm just repeating it again, just to make sure there is really nothing in the assignment. You just have to write and convince that the right spaces are there, and it will follow immediately. Everything will follow. I mean, it is just the same thing as the proof of LP is a Banach space, and the Cauchy sequence has a limit. If you look at it, it's precisely those will be the Cauchy sequence here. Okay, yeah. So is there a chat? Okay. What is there in chat? Is it? Oh, is my voice breaking?
Yeah, it was breaking a few seconds ago, but now it is fine.
Now it's okay. I'm sorry about that. I have two internet connection. One is from the BSNL, which really there is some problem. I have to go and complain. So I'm just hesitating to go there because I don't go anywhere. So I'm just hesitating to go there. I have to go to the BSNL. I'm not able to solve it by calling them. So I have to go there. Let's see. I have another one which is Airtel, but that's like a mobile. So it's like that. If it breaks, you tell me. I will repeat it. Okay. So this is same as the assignment. Anyway, I will post these notes so you can really see that. It is just saying that if you have a family of Banach spaces indexed by I, then you can create this X infinity, which is says all those vectors in the product such that the supremum is finite. So there is small correction to there is. I mean, I'm repeating this assignment because there was some mistake in the assignment. That's why I'm saying. So I said that if you use the P norm, you will get L infinity. You will not get L infinity. You will get something called C0. So I mean, if you see, even if you take a sequences, if you take sequences with finitely many entries, not sequences, you take sequences, family of real numbers indexed by natural numbers. If you consider all those sequences with only finitely many elements non-zero and finitely only element non-zero, everywhere else it's zero, then the closure with respect to L infinity norm is C0, sequence converging to zero, not the L infinity. Okay, so in the last assignment, I said it's L infinity, but that's a mistake. So which I realized, so that's why I'm repeating this assignment. Okay, so you take a family of Banach spaces Xi, then you take consider the direct product of that Xi, which you can form. Then in that direct product, you take all the elements which are bounded. I mean, all the tuples which are bounded. Okay, bounded in the I, in the each coordinate. The coordinate was bounded. So that is an L infinity that will form a Banach space. It's easy to prove. I mean, it's the same as L infinity is a Banach space. Okay, it's the same thing as that. You can prove it if you wish. And then there is then I am considering summation Xi, which is just you take all those tuple which which is equal to zero except finitely many entries, which is non-zero entries are finitely many. You define norm p on that as usual, like the norm p. Then you complete it. Okay, and that completion is precisely all those tuples whose coordinate wise is p convergent. Okay, so that's what I wanted to prove. And if you complete it in the infinity norm, that is the C0. For C0, you can consider the J itself. I mean, the uncountable also you can say what is C0, but then let us. I mean, you have to using finite net. You have to do it. Okay, the finite net, that sequence should converge to zero, or otherwise you can take it. The whole thing also you can take it to be countable if you want. Okay, if you don't find, because I haven't done nets, or if you haven't done nets anywhere else in any other course, then you can do it for. Sequence, you can assume I is countable. Okay, so this is assignment which is straightforward. Okay, so that assignment will imply that if you have we have defined orthonormal basis. I said that so if you define if EI is an orthonormal basis, O and B for H, then H will look like this. This is what I said. CEI. You can prove it. CEI is a one-dimensional subspace spanned by EI. I mean, it's just EI multiplied by complex numbers. So you can prove that from that it will follow, and all the properties of the OIMB which I listed last time will follow from that essentially. But still, to make it very more clear, I asked someone to present this. Okay, this presentation. This is just lemma 2.3.4 and 2.3.5, which are very easy, which are the straightforward lemma proposition. So from VS Sundar spectral theory, someone should come forward to present this. Okay. Okay, so this is something I noted and I am telling you. So in this class, we will continue with what we have done last time. Last time we proved Rees lemma. Okay, so we proved Rees lemma, which says that Rees lemma. This says that there is every linear functional is given by H itself. H is a Hilbert space. So this which says that for Hilbert space H. Okay, the H star is anti-isomorphic. Okay, it's isomorphic except that the linear map is not. The map is not linear. The map is anti-isomorphic to H itself. That is, there exists a map phi. I don't know what notation I used last time, but let me use this phi from H to H star. Okay, which is antilinear or conjugate linear. I don't know what I said last time. Which just means that phi of alpha x plus beta y equal to alpha bar phi of x plus beta bar phi of y, which is antilinear for all xy in H, and it's isometric. The linear functional phi of x is the linear function. It lands up in H star. Okay, it's same as norm x. Okay, and it's an isomorphism. It's bijection. Okay, so this we proved last time, and we want to make use of that. So what we want to do is the following. So we want.
Sir, sir, this antilinear isomorphism, we could also take I mean, so like, can't we come up with a isometric isomorphism in the normal sense by some other map, may possibly?
No. So for the linear functional, no.
Yeah,
See,
I mean,
point
so
is, you
H
can come
is
up with other
isometrical.
map. This map is anti-linear. You can come up with other map because between
Yeah,
the
this
Hilbert
is
spaces there can be any isometry. No, I mean for example, if H is what is this? H and H star will have the same dimension. No, they will have the same dimension because see, first of all, the anti-linear
yeah.
will imply that they have the same dimension in the sense the cardinality of the orthonormal basis is the same. So there will be an isomorphism between them anyway. But then what we want to say is this.
Yeah, so like, I
H and S star are always isomorphic. Okay?
so like,
Because they are the same.
yeah, so what I was asking was, is there any direct isomorphism between them, or like, do you need to go via that orthonormal basis
There
and
is
all
no
those?
there is no canonical isomorphism. Is that what you are asking? There is no canonical isomorphism. Okay? Between linear maps and this. There is
Okay,
no,
so this antilinear thing is quite canonical, right? But
this is canonical isomorphism.
I mean, the linear thing won't be canonical.
Yes, this is a canonical isomorphism. There is no canonical isomorphism. But anyway, H and H star will be isomorphic because they have the same dimension. Whatever dimension means. Dimension is just the cardinality of the orthonormal basis. Okay. So because of that, they will be okay. So
yeah, thanks.
So okay. So what are we at? So now I want to get a prescription for defining linear operators. Okay. So I have already said what is a sesquilinear form. Okay. Sesquilinear form is just here. Let B from H cross H to C be a sesquilinear form. It's like an inner product. Okay. Linear in the first variable, anti-linear in the second variable, which I defined in the very first class on Hilbert spaces, sesquilinear form. Okay. And then there exists, if this is a sesquilinear form, then maybe call this as proposition, which follows immediately. Then there exists a linear map. Now, let me make a different statement. Okay, let me first say make this observation and then make the statement as a proposition. Okay. The statement is this is a sesquilinear form. Corresponding to this sesquilinear form, there exists a linear map, okay, which I call as TB from H to H. You can have K here, no problem. You can have a sesquilinear form from K. Then this will be to K. Okay. Such that T be acting on any X. Maybe that should be H cross K. Let us see. TB, let me write it and then TB at X such that TB at X Y should be, it should be the other way, P of Y, so it should be K cross H. Or I can write it as, let me write B of X Y itself. I will write this the other way. X comma T Y. It cannot be X comma T Y. So P of this will not work. No? Txy is the linear form I want to get, and that is equal to bxy bar, byx bar, bxy bar. What is that I want to do? It's not there. For each x, I want to get a linear map Tx. Unnecessarily getting confused. For each x, I want to get a linear map, linear functional, which is Tx. Tx acting on y. This is my sesquilinear form. So Tx will land in B. So it should be B of what is K doing there? Yeah, so sorry. This is xy, yeah, x and y bar. This is fine. This is fine. Sorry, that's all. Y is in K. Okay, this is fine. So for x in H and y in K. This okay. I was unnecessarily confused. Okay. So I'm saying you have a sesquilinear form from H cross K.
Sir, what is T?
What is B? What?
T, I mean, you have defined TB. Is that TB?
TB is.
No, I mean, you were, yeah, TB.
There exists a linear map TB such that TBXY equal to this. Okay. Is this fine? I have a sesquilinear form from H cross K to C. Okay. Then corresponding to the sesquilinear form, there exists a linear map TB from H to K such that you take the TBX, the inner product of TBX with Y. Okay. So this is the inner product in K, right? TBX is in K, Y is in K. Okay. The K equal to B of X1. Okay. Or we can say that this is a sesquilinear form and this sesquilinear form is equal to that. Let us come to that. First, I want to say that given its sesquilinear form, you can get this. This is just clear. So B of, yeah. TBXY. So, but I'm just one, because it's not linear. So that's why I'm looking at it. Such that TBX, this is okay. Yeah. That's a linear functional. That's right. So you take alpha here, then alpha will. So you have to need a bar here somewhere. Is this okay? Now it's linear. Given a x, I want to get a tx. Given a x in H, I want to get a tx in K. Okay, that tx is given by the linear functional. So the tx is a vector I want to get. That is given by a linear functional y going ytx. Okay, ytx is a linear functional. So it should be linear functional. For that, I need to get that this should be equal to this bar. Yeah. Now it's okay. Okay. This function, see this function, proof of this. This function y going to b of xy. Y going to b of, I mean, fix x in H. Okay. Then y going to b of xy is linear. Sorry, anti-linear. You take the bar, this is linear. Okay. I mean, fix x. Okay. Then y going to this is the linear. So this is given by a, so this is equal to x times some vector, because by Rees lemma, this is given by something. So you call that as tx. Sorry, here it should be y. What I'm saying, y. I fix a y. Sorry, I should fix a y. I'm sorry. I should fix a y, then let me complete that. Take x in H, then x going to bxy, bxy, then y going to bxy bar is linear. That's right. So this implies by Rees lemma there exists a tx in K such that b bar xy equal to y. Right? Okay, I was unnecessarily getting confused. So if you take x in H, okay, fix a x in H, then y going to bxy bar, y going to bxy is antilinear, y going to bxy bar is linear. So since this is a linear map, there exists, so x is fixed. So corresponding to that, there is a tx. Okay, I call that as tx. Then there exists a tx such that bxy bar equal to ytx. Now it's clear, I believe. Is it okay? Because I got confused in asking you. It's okay? Hello? Someone say it's okay or it's not?
Yeah,
Okay?
yeah, it's fine.
It's okay. Okay, very good. Okay. So now this is okay. So this is what I have been saying. Okay. So that this is the linear map. This is just a linear map. Okay. So the proof, the next proposition, this, so maybe another definition. Sorry. Okay. This proof is over. Okay. Yes, sesquilinear. This is definition. Okay. Yes, a sesquilinear form bxy is bounded if bxy mod is less than or equal to some k times norm x times norm y. And the infimum, as usual, we define the infimum of such case. As usual, define norm b equal to infimum of all k which satisfies this property. Okay, which satisfies this property. So that is what is called norm b. Okay. Then the proposition is there exists a bijection between, I mean, it's an, well, let's say bijection without the norm, that between b of any h and k to all bounded linear forms. Linear forms on h cross k such that norm t is equal to norm b. And so it's the same equation, I shouldn't get confused, the same equation, such that I can even write txy equal to dxy. So if I take the bar both sides, this becomes txy bar. If I take bar both sides, txy bar equal to, I can even write like this. I mean, the same thing I'm writing it here, txy equal to b bxy. If I take bar here, it will become txy. So I have to take another bar there. So that will become bxy itself, right? If I take bar here, it will become txy. If I take bar here, that will be bxy. So is this okay? Is this fine? If I change it?
Yes.
Okay, txy equal to bxy. So that's what I have said. So given it, so it's clear that, so given, so this is a sesquilinear form. Given any x and y, this is a sesquilinear form. So this map is a bijection is clear. Okay, I have to only check the norm. I mean, I have to check only the boundedness. This map, given any linear map, then this is a sesquilinear form. Okay, and given any sesquilinear form by Rees lemma, we have said that we have got that that gives a linear form. We only have to prove that this is a bijection. For that, notice for any linear map, any bounded linear map, t from x to y, this norm T is equal to supremum of mod of Txy with norm x less than or equal to 1, norm y less than or equal to 1. That's because, I mean, this is, you have to notice the proof of this is norm T equal to supremum of norm Tx, norm x less than or equal to 1. And that is same as whatever the linear map I defined in the Rees lemma, phi Tx, norm of phi Tx with norm x less than or equal to 1. But then that is same as the phi Tx is nothing but x norm y, x Tx, y Tx. You can take it, because you are taking modulus, you can take it whichever the way you want. With norm x less than or equal to 1, norm y less than or equal to 1. Okay, that's all. So this implies that norm T is this, and that is precisely the norm of that. So this implies B, norm of TB is same as norm of B, what we have defined here. Norm of B, we have defined it like this, which is the infimum of that. I mean, which is same as the supremum n. If you go through the same proof, it will be clear. Okay, which is same as this. Or you can define norm B like that. Okay. So I'm just saying, I mean, this lemma is trivial. I don't want to spend too much time on that necessarily. So I hope this is okay. Is this fine? The norms are, it preserves the norm, and any sesquilinear form gives a linear functional like this. Is this fine with everyone?
Yeah.
Okay, if you have any,
Yes.
okay, you can check it out. I can leave this exercise, okay? Yeah, say it again. Yeah, you said something. Anyway, so this is what I want to say, that if you have any sesquilinear form, then it determines a linear function. Okay. So there is one thing I want to say is any quadratic form, which it determines an operator. So this is an observation or lemma, or maybe a proposition. Let H, so it's important that let H is a complex Hilbert space. It's not true in real Hilbert space. Complex Hilbert space. Let me add. One second, I'll come. Yes. Yeah. Yeah. So suppose if we have a complex Hilbert space, then S and T are two operators in H. I mean, it should be, it's a B of H. It's an operator from H to H. Okay. B of H. Then, so S and T and, sorry. I mean, see, we know that if Sxy equal to Txy, then S equal to T, because the sesquilinear form coincides. You know that the sesquilinear form determines the operator. So, I mean, it's clear that because of, due to Rees lemma also, it is true. If Sxy equal to Txy, then that implies that S equal to, we will go through that also here. I'm saying that if it is true for Sxx, the inner product between Sxx and Txx, they are same, then also it is true. Okay. So then S equal to T as operators. So proof, it is true only for a complex Hilbert space, not true for real Hilbert spaces. So if consider B of xy equal to T xy, okay, or B SRT, whatever, B of xy equal to T of xy, then consider this kind of sesquilinear form, then polarization identity. You have the polarization identity. polarization identity applied to this B of xy, which says the following, which says that B of xy equal to summation I power k B of x plus iy x plus iy. Okay, so this should be true for all x. Okay, for all x. So k equal to, this is I is the complex number I, k equal to 0 to 3. Okay, so because of the polarization identity, I mean, you can, I mean, for S and T, both S and T, you consider the polarization identity Tx by Bxy given by this. This says that Sxx equal to Txx. So in particular, yeah.
There should be a factor of 4 somewhere, right?
Yeah, that should be a factor of 4. Right?
In the identity.
Yes, so 4 should be here. Sorry. 1 by 4 should be there.
And in the right hand side, it should be bx plus I power ky, comma x plus I power ky.
Yes, sure. Otherwise, there is no point. Correct. Yeah. Otherwise, there is no summation. Yeah, correct. So what I want to say is, I mean, you remember the polarization identity. The point is, if you know that Txx equal to this, then you get that Bxy equal to this. Considering this polarization identity, you get that Txy equal to Sxy for all x. You consider this polarization identity using that, using this Sxx equal to Txx. Using that, you can prove that Txy equal to Sxy. Okay. Now this implies that Tx and I mean this. So the point is, if I mean, this is something we must have noticed earlier, that if you just take, if some xz equal to yz for all z in H, then x equal to y. Just take, I mean, this is because you have to prove that if x is equal to 0 for everything, then x is 0. That follows because you just take x equal to x. Okay, I mean, z equal to x. Okay, that will give norm x square equal to 0. So, I mean, this just implies that x minus y z equal to 0. So take z equal to x minus y. That will imply that this is equal to, I mean, these two are equal means that x equal to y. So because of that, we get Ex equal to Tx equal to Sx. That's all. So we use polarization identity to do this. And if for real Hilbert spaces, there is no polarization identity. So because of that, we cannot use that. So for example, counter example, in real Hilbert spaces. So real Hilbert spaces, the counter example should be the following. So what do we want to do? I want to prove that. So example for in real Hilbert spaces. H over R. Okay, this is not true. So even in finite dimension, this is not true. I want to get an example. I think this will work. Just this. 0, 0, minus 1, minus 1, that's why. So this says the following. This is 0, 1, minus 1, which is just your product between these two. So this is equal to 0, right? Because it's real. Okay. I mean, for complex, this is not true. For real, this is true. But so this implies that this inner product is 0 in R2. Okay. So this matrix, but this is not 0. Okay. This matrix, which is an operator in R2, which satisfies that Txx equal to 0 for all x, but this is not 0. So this is a counter example that this relation holds only in complex Hilbert spaces. Okay. So now we want to use the Rees lemma. We want to use that sesquilinear form identification to the adjoint. So definition: T is an operator in P of HK. Then define T star from K to H by T star of so maybe I use y x equal to y of dx y in x and h. This is clear because this gives a sesquilinear form. This gives a sesquilinear form, and any operator is determined by the sesquilinear form, and this is bounded because t is bounded. So t star is well defined, and t star is a operator. Then I will go through this quickly. Okay. Then the following is true. One. So what are the alpha why this okay. So you must have seen these things in linear algebra. It's the same thing. Okay. So is there any other property you can tell me? Norm of t star t equal to norm t square. This is what is called C star identity, which you will see later. It's in the next course I will do this. C star identity. This is what is called C star identity. And this is fourth one. The third one is norm t the same as norm t star. Okay. Norm t same as norm t star. Norm t star t is norm t square. It's anti-linear and it's involution. Sorry, involution. It is an involution. Okay. T star star equal to t. So what else? Okay, one by one we can see. See, this t star is something which is determined by this property. T star yx equal to ytx. Okay. If any other operator satisfies this property, then that should be equal to t star because we have proved that there is a bijection between sesquilinear form and bounded operators. Bounded sesquilinear form and bounded operators. So using t, you define t star, which gives this bounded sesquilinear form. So t star is well defined, uniquely defined by this property. So if you just have to check that alpha t plus s. If you insert alpha t plus s here, then this alpha bar t bar plus s, because of the antilinear property, that satisfies this property. Okay, that's what you have to see, and you can see that this property satisfies. Just insert it. Okay, insert this in this equation, and you will see that that property is satisfied. Similarly, if we have a t, you can first, I mean, for example, you have this st star that's right equal to, so what I have written st star t star is, so yes, what I have written, nobody objected here. Star t star that's right equal to t star x this way equal to x t this way. Okay, this implies star t star equal to ts star. Okay, just you write it in the equation and you get this. And similarly, if you apply t star star xy, which is equal to t, you just have to take it there, x t star y, which is equal to txy. Okay, This implies T star star. Only non-trivial thing to prove is this C star identity. So can someone say yes to everything, whatever I said, except the C star identity? We have everything else is clear. I'm saying, is that fine? Okay, I assume it's fine.
Yes.
I assume it's fine. So, and also you can see that this is satisfied. T star xy equal to xty. Okay, and we know that norm T equal to supremum of this inner product Txy with norm x less than or equal to 1, norm y less than or equal to 1. So which is same as supremum of, you just apply it. I mean, it's just, you can have x t, I mean, if you take t star y here, then that's the same thing. It's the same thing as t star xy. Because you will get the t star here, t star yx, sorry, t star yx. If you wish, which is the same thing. So this implies norm T is equal to norm T star. So only thing we have to verify is, so only thing to verify, norm of T star T equal to norm T square. Okay, so this is the crucial thing we want to verify. So first notice that, so this is true for this, I think I forgot to say. So for any operator, for any S in B of H, ST I want to write, so maybe T, for any T in B of H and K, and S in B of K, KL, okay. Then norm TS, norm ST, sorry, norm ST can decompose S and T. Norm ST is less than or equal to norm S times norm. I mean, this is just clear, no? Norm ST equal to supremum of STX. Or we can just write this. We can directly do. Is less than or equal to norm S times norm TX. That's the property of the norm, which is less than or equal to norm S times norm T times norm S. Okay. So this satisfies, this is a K which satisfies this condition. So that implies that norm S, I mean, this norm of ST is the infimum of all such K satisfies this condition. So because of that, norm of ST is greater than or equal to norm of ST. Okay. So this is true. This also, you can notice that, I will come to this. Okay, I will come to that later. So because of that, because of this, norm of T star T is less than or equal to norm T times norm T star, okay, which is equal to norm, both are norm T and norm T star is same. So because of that, they are equal, norm T square. We have to prove the other way. So now let us take norm T square, which is equal to supremum of norm Tx, norm x less than or equal to 1, this square. Okay. But then this is supremum, that is equal to Tx square with norm x less than or equal to 1. Okay. Now I have to prove that this Tx square is less than or equal to that. So Tx square, which is equal to Tx, and which is equal to T star. Sorry. This is equal to T star Tx. And this is, so this is less than or equal to T30. If you want, you can use Cauchy's phosphorus. And that is less than or equal to this. Okay. So this, so instead of here, I get this. Okay. The norm x square is less than 1. So this implies norm t square is less than or equal to norm t star. So we have proved the other way. Okay, it's fine. Is that clear?
Yes.
Okay.
Yes.
Okay. So that's all for adjoint. Okay. We have defined adjoint. We have studied its property, same as what you have seen in linear algebra. And you have this norm t star t, important identity called C star identity. This norm t star t same as norm t square. Okay. Then I want to introduce some property and finish the Hilbert space today. Okay. So next thing is projection. This also you must have seen it in linear algebra, but here there is some more property. Projections. So if M is contained in H is a closed subspace, then H looks like this. We have already seen that H looks like M direct sum M per. Okay. So let X in H and X equal to Y plus Z. Y is in M, Z is in M. Then define P of X equal to Y. Okay. This is certainly linear, clearly linear, and norm Px is equal to norm Px equal to norm Y to the square, which is less than or equal to norm Y square plus norm Z square, which is actually equal to norm X square. Okay. So this implies norm P is less than or equal to 1. Okay. So this is bounded. So we have this operator, and this is what is called, maybe I will put a M in the bottom. Okay, so this is what is called a projection onto the subspace M. So if you have a subspace M, then you can define this operator by this prescription, Pmx equal to Y. Any x can be written as y plus z, where y and z are orthogonal. Then you can define Pm of x equal to Y. Then we have proved that it's a bounded operator which satisfies this. Further, it's an idempotent, P square equal to P. That is just clear. If you use P of x equal to Y, okay, which is equal to Py, but then Y is already in M, so this is equal to Y. P square equal to Py. Okay, this is one thing. Further, and P star of any xy. Okay. Maybe I will x prime I use x prime. So for x equal to y plus z, x prime equal to y prime plus z prime. Okay, then P star of xy equal to x p of x prime, p of x prime. That is equal to y plus z, and p of x prime is just y. But then y prime is, z is in M prime, y is in M. So this is in M, this is in M prime, sorry, M per. Okay. So y prime is orthogonal to z. So this is equal to y prime. But then this is same as p of y prime. But this is same as, since p of y is orthogonal to the z, this is same as p of y. Here you can put, if you wish, you can put here, add another one, y prime plus z. You can add this. Okay, because it's orthogonal, it's the inner product is 0, so you can add that. So this is equal to 0. This is equal to py. You can put x prime. Okay, so sorry, pz, px. This implies p star equal to p. So this is what is called self-adjoint. I think I forgot to define what is self-adjoint. This is what is called self-adjoint. That is P is self-adjoint. Okay. Is it clear? The proof of P is self-adjoint is clear. I've just used the fact that we have used the fact that P star X, I mean, we are using this equation equal to Pxx. I've gone through this calculation. P star Xx prime equal to, I'm just taken the P there, so that is P here. So which will give me Y prime there, and which is, but then the inner product is Y prime there. But then you can keep P here, that also give the same value. Okay, so P is self-adjoint. So P satisfies this thing. So maybe I'll put a M here. I mean, I have used P, but it's what is called PM. Okay, using a subspace, we have defined this. So this is a projection. Okay, so these are all the properties of projection. I want to prove the converse. Okay? Proposition. There is a given P of H such that P square equal to P equal to P star. Then there exists a M contained in H closed subspace closed such that P equal to P. That's all. I'm going fast. If you have any problem, you stop me. Okay, it's not clear to me whether I'm doing very elementary things or I'm going fast, which is not clear to me. Okay, so since I don't see any of you, it's not clear to me. You have to tell me if you don't understand anything or something. Otherwise, I assume. I'm thinking that I'm doing very elementary things for you. Okay. So given any P which satisfies this, then there exists a subspace which satisfies that. So you have to take M equal to, given a P is given, so I take M equal to range of P. Okay. So first range of P is closed, that is clear. M equal to range of P, P equal to range of P. Then if X is in M, X is in range of P, that is M is in range of P, then there exists a Y in H such that X equal to Py. Okay. Now P square X equal to P of P square Y. So, no, not that. Now Px equal to P of Py, which is equal to P square Y, but that is same as Px, right? That is same as Py, so which is equal to X. So we have Px equal to X. Okay. So if Xn converges to some X with Xn containing in X M and X in X and M, then Pxn, which is equal to Xn, of course, okay, which also converges to X. Okay, so this implies Px equal to X. P is bounded, so Px equal to X. So this implies X is also in M. So M is closed.
So Pxn converges to Px, right?
Pa converges to Px, but that is equal to X. Pxn equal to Xn. Xn converges to X. Pxn converges to Px. Okay, then Px equal to X. So okay, Pxn converges to Px, right? So yeah, right. I have to insert a P here. Okay, but then Xn converges to X also. So Px equal to X. Okay. This in particular implies X is in the range of M. So this that's what I'm using. So X is in M. I'm saying M is closed. Is it clear? Is this okay?
Yes.
Okay. I'm just proving that M is closed.
It's fine.
So M is closed, number one. And we have to verify that these two are same. Okay. So what do you have to verify? So we have to verify that, we verify that P and see H equals M direct sum M. We just verify that P restricted to M is same as PM. P restricted to M prime is same as PM. Okay. PM is P is the given operator which satisfies the idempotent property and self-adjoint property. P equal to P square and P equal to P star, which is our P. We have PM. PM comes from the M. Okay, where the M is, we have given the M. We have to prove that PM and P are equal. So we have just proved that M is closed. Now we want to prove this.
So
yeah.
So in the first step, we proved that for all elements x in the range, we have px equals x. Right.
Px equal to x. Correct. No. The first thing, first is correct. In the first step, we have proved that up to here, we have proved that x in M, then Px equal to x. Correct.
So in the second step, we are taking a sequence xn
Sequence
tends to
in
x.
xn in M. Okay. Suppose xn converges to x, then Pxn converges to Px. But then Pxn equal to x, so Px should be equal to x. Okay. So x is also in M.
But then if Px equals x, if Px equals x, how can we say that x is in M? Like we proved
x
the
is
opposite
defined as the range of P. Px equal to x means x is in M.
Okay,
M is defined as range of this. Okay. So I have to prove that x is also the range of M, range of P. Okay. So that's what it means.
Yes.
Okay. X equal to any Py is enough, but x is equal to Px itself. Okay.
Yeah.
Okay. So that's what I have said. Okay. Now, so we prove P restricted to M equal to Pm. Okay. And P restricted to M per is also Pm. Okay, that's what we have to prove. I mean, you can take the sum if you wish. Okay, I want to prove these two things. Then it is true for sum, and that's what H is. So now P restricted to M we want to prove. Of course, we know that P restricted to M is identity, and PM restricted to M is also identity. Okay, so this is clear, right? We have already proved that Px equal to x for all x in M. Okay, PM also when restricted to M, it's PM is defined as PM is defined by that, no? Pmx equal to y, the y which comes from M. Okay, if x is in M, then Px equal to x, Pmx equal to x. Okay, so this is clear. We only have to prove that they coincide in the orthogonal complement. Okay, so suppose Z is in M per. Okay, then x we have to prove. I want to apply Z. Okay, Pz equal to P star Z. So P star x x is Z, but P star is same as P, which is equal to Px Z. And x equal to y plus, there is Z here, so I want to use something. Z prime, okay, y prime is Z prime, y prime is in M, Z prime is in M. Okay, okay. Now px, okay. Now this is equal to y prime Z, but then this is 0 because y prime is in M and Z is in M prime. Okay, so this is 0. So this implies Pz equal. This is true for all x. Okay, this is 0 for all. The x is arbitrary, so this is true for all x in H. So this implies Pz equals 0. On the other hand, Pm acting on any Z or Z in M prime is also equal to 0 because PM is just, if you write y, this is the Z, you can write it as the y corresponding to it is 0. Okay, so PM of Z equal to 0. So this implies P equal to. This is okay. This is very easy. Is fine.
Yes.
Okay, I would like to hear more voices or ask some questions. Okay. This is same as what we have done in linear algebra. It's my duty to go through this, so I am going through this. Okay. So that's all about projection. So this is what we have defined as projection. and there is a one-to-one correspondence between, I mean, projection is you defined as an operator which satisfies p square equal to p and p equal to p star. Self-adjoint idempotents are called projections. Okay. Then there is a one-to-one correspondence between closed subspaces. This is the difference between linear algebra and functional algebra. In functional algebra, it is just subspace. Sorry, in linear algebra, not linear, finite dimensional linear algebra, it is just any subspace will give. Here you have to take closed subspace. Okay? If it is not closed, then there will be a problem. Then there will, I mean, the closure will have also project. I mean, the projection will be on the closure of it. Anyway, so what do you want to do? So we have done projection. Now I want to do isometry and unitary. So these two things I want to define, and then so isometry. What is an isometry? Isometry is something which preserves the norm. Okay, that's what we have defined as isometry. Okay, so by polarization inequality, it will preserve in the Hilbert spaces. It will preserve the inner product also. Okay, something which preserves the norm will preserve the inner product also because of polarization identity. So a unitary is just a surjective isometry. But then in infinite dimensional and in finite dimension, if you have an isometry between h to h, then that will be onto. Okay? But in infinite dimension, that will not be the case. So the property of the isometry is it preserves the norm, it preserves the inner product, and then it's equivalent to saying it takes orthonormal set to orthonormal set. A unitary is something which takes orthonormal basis to orthonormal basis. Okay, so the following are equivalent. So the following are equivalent. One for something u in p of h and k. Maybe I can take 2 h and k, doesn't matter. H and k. So what is the for? For all orthonormal set ei, maybe not a basis contained in H. Okay, uei is also orthonormal. There exists orthonormal set ei such that uei is orthonormal. Ux uy equals h for all x y h. So norm ux equal to norm x for all x and h. U star u equals identity. This one is the identity operator. Okay, identity. Okay. This is the identity operator. So these are all. This is very easy. Of course, 1 to 2 is clear. That says for all orthonormal bases, there exists an orthonormal basis. That is clear. Now we consider this. So 2 to 3. 2x, 2y.
Sir, what is written in 2 towards the end?
Towards the end.
Yeah, UEI is an orthonormal. I can't read beyond that.
UEI is also orthonormal. EA is orthonormal set, then EA is also orthonormal. Okay. Okay.
No, sorry, then what's the difference between 1 and 2?
1 says for all orthonormal set, 2 says there exists one orthonormal set which satisfies that.
Oh, okay.
That's the difference.
Okay.
Okay. So I want to talk about inner product between x. So, ux uy. Okay, that's what I want to calculate. So let x equal, so any x will look like summation x ei with respect to orthonormal basis or eix. Xei, correct. Whatever. I'm confused with the physics in the product. Xei, x, right? Xeax or eaxx. I think this is correct.
xi times ei, right?
Sorry, sorry. I was concentrating here. I made a mistake there. No, this is okay. No, xei, not eix. This is okay. I believe. Okay, and y equal to summation yei. Yeah. Okay. Okay. Then ux ui. Okay. You have to apply x and y. You have to apply ux here. You have to apply ux here. You have to apply u on this y. But these are all scalars, and this is continuous. You can take it with. I mean, let me skip all the steps and write summation over I and j x ei ei y, or the bar of that ei y times u ei u ej. Right? Okay. If I just apply is substitute x and y, then it's an infinite series. I mean, here it varies over I, here it's over j, maybe you wish. Okay. The same indexing set. Okay. Then you will get from here you will take it out. You can take the xei and the xej. You have to take it as a bar, so you get these things. But then this is non-zero only for I not equal to j. This sum surveys only for I equal to j. So this is summation over. This is summation over I. Yeah, I. So x ei ei y. I mean, we have that uei and uej. They are I mean, they are orthonormal. That forms an orthonormal set. So uei is orthogonal to uej. So it's just it surveys only for that.
So how do you get that UEI and UEJ are orthonormal?
That is the
Because
function of 2.
because by statement 2 we have that there exists an orthonormal
Yeah, you
set
fix for
such
that
that
orthonormal.
the image is orthonormal.
Yeah, you fix that orthonormal set. That's why I'm using. What is the problem?
So but here we are taking a basis, right? Not like
EA
we
is
are.
a basis. You take EA as a basis. Oh. Mm,
So if we assume in statement 2 that there exists an orthonormal basis such that the image is orthonormal
correct.
set, then we are fine.
You are right. Yeah, that's what one should have. I'm sorry. That's what is correct. You are right. I mean, it doesn't make sense, no? The first statement makes sense for all orthonormal. The second thing, it does not make sense. Even a single element is an orthonormal set. So if that is orthonormal, that doesn't make sense. So that
Yeah.
orthonormal basis. That doesn't make sense. Orthonormal basis. It should be basis. You are right. Okay. Yeah, otherwise you can take a single element. So if A is an orthonormal basis for H, okay, that's right. So then we get this. We are taking the orthonormal basis and we have this. That's right. Okay. So now this is what I have done. X E I E I Y. Now this is just inner product between X and Y. Right? Which you have seen. This fine? Okay, I assume
Yeah.
3 implies 4. We have that ux uy equals xy. I mean, no. Maybe I should have said the other way. So 3 implies 4 is clear. That is clear. 4 implies 5 is not whatever. Clear. 4 implies 5. So this implies you, I mean, maybe I don't even need that. I have to see that. We have ux, ux ux equal to xx. Okay, the norm is preserved. So this implies u star, you can bring the u here, u star u xx equal to identity xx for all x. But then any operator is determined by the quadratic form. That's what we noticed. So u star u equal to h. Okay. Now we have to prove the other way. Phi u implies 1. So you have to verify that if you have any orthonormal set, then so if vi is orthonormal.
So here we are assuming that the Hilbert spaces are complex, right?
Correct. Correct.
Okay. Because otherwise, like the polarization
Otherwise,
identity
otherwise you
couldn't be.
don't have these things. From inner product to norm, you don't have. Polarization, this itself you don't have. Otherwise, you have to assume that it preserves the inner product. You are right. So you see,
Yeah.
you can work with real also, but then you will not have that it preserves the inner product will imply it preserves the norm. Okay.
Yeah. Yeah.
So that's what you have, that's the difference. Okay. So we will work with complex. You just make sure that the difference is that. Okay. You have to assume that it preserves the inner product, then this will be true. Okay. Then it will it will satisfy the bilinear form. The bilinear form will be equal. So so suppose UA is an orthonormal set. Okay. Then UEI UEJ equal to U star U EI EJ. So which is identity, which is equal to EI. Okay. So it's all clear. Okay. These are all very easy. So we'll just go into. Next proposition is U is an isometry. It's isometry. Then the following are one, U takes Y and B to Y and B, all Y and B to Y and B. Orthonormal basis to orthonormal basis. U takes some Y and B to Y and B. Is super some orthonormal basis to orthonormal basis. Okay. Three, it preserves the inner product and all those things are clear. So, it's isometry, so it should preserve the inner product. U is surjective. U is invertible. Invertible means with inverse U star. Okay, with inverse U star means U star U equal to identity. That's what we had. But then, and also and U star equal to 1. Okay, that's what invertibility means. U and U star are mutually inverse. Did I say this is the property of isometry? Okay, or anything which satisfies this property is called isometry. Anything which satisfies this property is called unitary. An isometry which is surjective is called unitary. So that's why this proposition is. So U is invertible. Then fourth is U is onto. Okay. The proof is trivial. So U takes orthonormal basis to orthonormal basis. You take some orthonormal basis. 1 to 2 is clear. So if it takes orthonormal basis to orthonormal basis, then U star U, that's just clear. Then it's isometry. So already U star U is identity. We have to verify that U star is identity. But U star of any X and Y, X can be written as orthonormal basis. So that EI, Y and B. Okay. Then this is equal to summation over IJ. So you want to, so this is equal to U star X, U star Y. Okay. And which you can write it in terms of the orthonormal basis, which is U star X EI, EJ, U star. Sorry, U star. Yeah. Now this is equal to summation ij, which is X, U of EI, U of EJ. What I have done? U star X, U star Y. That's right. And U star X, U star. I will. Yeah, this is okay. U J Y. I mean, you write it clearly, so that will become X1. Okay. Okay, this is trivial. Of course, if it is invertible, it's onto. If it is onto, since it's an isometry, it will take. I mean, if it's not taking orthonormal basis to orthonormal basis, then there will exist something which is not, which is orthogonal to the whole thing. I mean, it's clear. Okay, it will not be the possible. Should I do that? It's clear now. So this is all about unitary.
Yeah, it's fine. Yeah.
Okay. So I will stop Hilbert spaces with this. There are some few more things to do, but we don't have too much time. So I will stop with this. I want to ask you the following. So have all of you, so I don't know how many people are present here now. So I want to know whether all of you have done, so there are only 10 people. So anyway, I will write a mail also. So have you done Fourier series? Because it is done in analysis 2, in the analysis 3 for BSc students. Okay. So I don't know whether all of you have done Fourier series. I mean, the discrete Fourier theory. If you have done that, then I will not do that. I mean, in my course, I have done it. It's done in the analysis 3. So those MSc students and PhD students, so who are especially not from CMI, if you haven't done Fourier series, then I will do. Otherwise, I will not do that. I will directly do Fourier transform for real line. Fourier transform, Fourier analysis for real line, which is also very small amount. Since we don't have any time, I don't want to repeat that. So I don't know who are all here. If anybody really wants me to do that, you tell me now. You can reply it in an email also. Okay. Okay. So it's 6:19. I will end the session. So I will write a mail about exam anyway tonight, and also ask this question. Okay.
Sir,
Yeah.
Sir, I was just wondering, so is there any concept of adjoint for maps between Banach spaces?
Sure. But it will be from different spaces. So if you have X and Y are Banach spaces, T from X to Y, X, Y, Banach. Okay. Then you can define a T star from Y to X. Okay. Which will satisfy all this property, which with C star from Y star to X star, such that T star acting on any phi equal to phi of Tx. It is just basically, it is this definition you are using there.
Okay, so like in Hilbert spaces, this H is isometrical isomorphic to H star, and therefore working with H and X, I mean H and K here works.
Exactly, correct.
I see.
Yeah, so you can define it like this.
So like, does this adjoint have some good properties? Like, does that make B of H or B of X a sister algebra or something like that?
What do you mean by sister algebra? Because it's in different spaces. B of how will it make? Because
no, I mean for a same Banach space, if you like try to work with.
No. What is the, if it is same Banach space?
Okay, so yeah.
Star is from some different spaces. Yeah. So how will you have a star?
Yeah, but I mean, what if it is reflexive or something like that?
No, reflexive means X star equal to X. It's not X star, it may not be equal to X. Right? Reflexive means double dual is X. That's what reflexive is. We are supposed to do all that, but we don't have much time. We have only the next month, 3 more weeks. So I didn't do all that. Okay. So no, you can talk about such things, but it's very, I don't know, but it's not in the usual way.
Okay.
Okay then.